On July 20th, 1976, the Viking 1 lander scooped a handful of Martian soil, mixed it with a nutrient solution, and waited. If there were microbes in the soil, they would start eating and releasing gas. The instrument detected gas. The experiment returned a positive result. 48 years later, we are still arguing about what it was. For most of the 20th century, the honest answer was, we have no idea. For a brief, embarrassing window in the 1970s, we thought we might find out. NASA landed 2 Viking probes on the Martian surface, scooped up soil, and ran biology experiments directly on it. The results were confusing. Some instruments suggested metabolic activity, others suggested nothing of the kind. One experiment released nutrients into a Martian soil sample and detected a burst of gas, exactly what you might expect if microbes were consuming the food. But another instrument, designed to detect organic molecules, found almost none. The scientific community, unable to reconcile the contradiction, concluded that Martian chemistry was unusual but lifeless, and quietly moved on. Except the question never went away. Here is what we actually know about Mars today. The surface is not friendly. The atmosphere is 95% carbon dioxide, thinner than the air atop Mount Everest by a factor of 100. Average temperature sits around minus 60 degrees Celsius. Liquid water cannot persist on the surface. The pressure is simply too low, and any water that appears instantly either evaporates or freezes. And there is the radiation. Without a global magnetic field and without a thick atmosphere, the Martian surface is continuously bathed in cosmic rays and ultraviolet light at intensities that would shred bacterial DNA within hours. A human standing on the Martian surface without a spacesuit would receive a lethal radiation dose in a matter of minutes, long before the cold or the thin air finished the job. So, no life on Mars. Obvious conclusion, except we are asking the wrong question. We keep imagining life on Mars the way we imagine life on Earth, at the surface, in the light, breathing the air. But that picture, even for Earth, is embarrassingly incomplete. Consider what lives beneath our feet. Not just earthworms and soil fungi. Go deeper. Go several kilometers down into the continental crust, into porous rock, saturated with ancient groundwater, into environments that have never seen sunlight, never felt a temperature above a few degrees, never had access to oxygen. In those depths, there are microorganisms, billions of them, per gram of rock in some places. The total biomass of Earth's deep subsurface biosphere is enormous. By some estimates, it rivals or exceeds the biomass of everything living on the surface combined. And here is the truly remarkable part. These microbes do not depend on the sun. They do not eat sugars produced by photosynthesis. They feed on hydrogen gas seeping up from the crust. They consume carbon dioxide and produce methane. Their metabolism is so slow that a single generation takes not hours but thousands of years. In samples of ancient water sealed inside South African gold mines for millions of years, sealed entirely from the surface world, microbiologists have found flourishing communities of bacteria living on chemical reactions sustained by the decay of radioactive minerals in the surrounding rock. These organisms have been completely isolated from the rest of Earth's biosphere for timescales longer than the existence of multicellular life. And they are fine. There are also the organisms of the mid-ocean ridges hydrothermal vent communities that build entire ecosystems on chemical energy from the ocean floor, running on hydrogen sulfide rather than sunlight, thriving at temperatures above 80 degrees Celsius in water so hot and pressurized that it would scald and crush any land organism instantly. And there are the microbes living in the deep brines beneath Antarctic ice sheets, in films of liquid water maintained by salt and pressure at temperatures well below the normal freezing point of water. There are bacteria in the stratosphere. There are organisms in the cores of nuclear reactors. There are microbes that eat radiation and excrete it as metabolic byproducts. The surface of a planet, it turns out, is not where life has to be. It is just where life is easiest to see. Now, think about Mars with this in mind. Mars today is cold, irradiated, and dry on the surface. But descend 50 meters below that surface, and cosmic radiation can no longer reach you. The rock above acts as shielding, the same way that the meters of water above a deep-sea vent community protect the organisms from the radiation environment of the surface ocean. Descend deeper still, and geothermal heat begins to warm the surrounding rock. Not to comfortable temperatures by human standards, perhaps, but to temperatures where liquid water, especially salty water with a depressed freezing point, can exist. And there is evidence it does. Radar measurements made from Mars orbit, specifically from the European Space Agency's MARSIS instrument aboard the Mars Express orbiter, detected a reflective layer beneath the southern polar ice cap, consistent with liquid water. Briny, extremely cold, pressurized, but liquid. And wherever on Earth we have found liquid water, even in environments that seem completely hostile to anything resembling life, we have found microbes. Every single time, the equatorial surface of Mars, meanwhile, is not as uniformly terrible as it sounds. During summer afternoons at low latitudes, temperatures briefly climb above 0 Celsius. The humidity is catastrophically low, the radiation high, the pressure wrong for liquid water to persist, but for temperature alone, those conditions are not dramatically worse than the dry valleys of Antarctica or the permafrost of Siberia. People live and work in Norilsk, where winter temperatures fall below -50. Microbes live in the permafrost beneath Norilsk, in the bedrock beneath the Atacama Desert, in the salt flats of the Danakil Depression. The range of conditions under which life on Earth can persist keeps expanding every time we look somewhere new and hostile. We keep finding life where we expected to find nothing. The question then is not whether Mars could support life. The question is whether life ever got started, and this is where the story gets genuinely complicated. 4 billion years ago, Mars was a different planet. It had a magnetic field protecting its surface from the relentless pressure of solar wind that would otherwise strip the atmosphere. It had that thicker atmosphere, enough pressure for liquid water to flow freely. It had rivers, not the metaphorical kind, but real river channels wide enough and deep enough to be seen clearly from orbit, carved by water flowing across the surface over millions of years. There were lake basins. There were deltas where rivers emptied into standing bodies of water. There may have been a shallow sea covering much of the northern hemisphere, a body of water whose ancient shoreline can still be traced in the topography of the planet. Conditions on early Mars were not dramatically different from conditions on early Earth, warmer, wetter, geologically active, and on early Earth, life appeared. We do not know exactly when or how, but somewhere around 3.5 to 4 billion years ago, chemistry became biology. Whether the same thing happened on Mars, that is the crux of the problem. Because we have exactly one example of life emerging from non-life, and that example is us. From a single data point, you cannot calculate a probability. This is a genuine epistemological limitation, not false modesty. Life might be a near inevitable consequence of the right chemistry given enough time in liquid water, a process that runs reliably wherever the ingredients come together, like fire running reliably wherever there is fuel and oxygen and heat. Or life might be an event of such staggering improbability that it happened once in the observable universe, on a pale blue dot orbiting an unremarkable star in a spiral arm of the Milky Way, and the rest of the cosmos is silent and dark and empty of anything that can think or feel or ask questions about itself. We genuinely do not know which of these is true. There is no experiment you can run with one data point that resolves this, which is why the second data point matters so much. Finding life on Mars, any life anywhere, even a fossilized biofilm in an ancient lake bed, would be one of the most important discoveries in the history of science, not because of Mars specifically, but because it would mean life is not a fluke. It would mean the universe makes life, the way it makes stars and galaxies, as a natural consequence of physics and chemistry given time. But there is a third possibility, one that is strange enough to be worth sitting with. About 3.8 billion years ago, Earth already had life. And at roughly the same time, a period of intense asteroid bombardment was striking the inner solar system, a period geologists call the Late Heavy Bombardment. Large impactors, bodies kilometers across, sometimes tens of kilometers, were hitting Mars and Earth and the Moon with regularity. When a large enough asteroid strikes a planet, it does not just leave a crater. It ejects material into space with enough velocity to escape the planet's gravity entirely. Rocks from the surface, carrying whatever was living in them, can find themselves drifting through the solar system. Some fraction of that material will eventually reach another planet. We know this happens. We have found meteorites on Earth that came from Mars, confirmed by their chemical composition and by gases trapped inside them that match the known composition of the Martian atmosphere. Blasted off the Martian surface by ancient impacts, drifting through the solar system for millions of years, and eventually captured by Earth's gravity. One of them, a meteorite found in Antarctica and catalogued as ALH 84001, was ejected from Mars approximately 3.9 billion years ago, right at the peak of the bombardment. This meteorite generated enormous controversy in 1996 when a NASA team announced it contained structures that might represent fossilized microbial life. The claim remains contested, but the meteorite is real. The mechanism is real. Life, if it existed on early Earth, may have been carried to Mars on debris from those impacts. Life, if it existed on early Mars, may have been carried to Earth. The two planets were exchanging material for hundreds of millions of years during exactly the period when life was first emerging. Mars, in fact, may have had more favorable conditions for certain prebiotic chemistry than Earth did during that era. Different mineral composition, different water chemistry, a surface that may have dried and re-wetted in cycles that concentrate organic molecules. There is a real and serious scientific argument that life started on Mars and seeded Earth, rather than the reverse. Which means it is entirely possible that life on Mars and life on Earth are cousins, or the same lineage, that we are in some deep biochemical sense Martians. That whatever lives in the Martian subsurface today, if anything does, carries the same molecular machinery, the same genetic code, the same left-handed amino acids and right-handed sugars that every living thing on Earth uses. And that asymmetry, left-handed amino acids, right-handed sugars, is one of the things that gives scientists a way to look for life they cannot see directly. In chemistry, many molecules can exist in two mirror image forms, identical in atomic composition, but not superimposable on each other, the way a left hand and a right hand are structurally identical and yet will not fit in the same glove. Chemists call these chiral forms. In non-biological chemistry, in the asteroid material that rains onto Earth, in laboratory synthesis without biological catalysts, both mirror images appear in roughly equal proportions. But life on Earth chose sides early and decisively. All amino acids in living proteins are left-handed. All sugars in DNA and RNA are right-handed. No one fully understands why life made this choice rather than the other. It may have been pure chance. Whichever chirality dominated in the first self-replicating molecule got locked in through inheritance, and everything that came after inherited the same bias. The key point is that this bias is detectable. If you grind up a sample of ancient Martian rock and analyze its amino acids, and you find a strong excess of left-handed forms, 90% say, rather than the 50-50 split of random chemistry, that is a chemical fingerprint of biology, not of living biology necessarily. Even a billion-year-old fossil, frozen in rock, would retain this signature. Amino acids are among the more stable organic molecules. They do not racemize, flip from one chirality to the other quickly at cold temperatures. The subsurface of Mars, perpetually cold and shielded from radiation, is an excellent preservation environment. A dead biosphere could leave legible traces for timescales longer than the age of the solar system. There is a second signature, subtler and equally powerful. Carbon exists in several isotopic forms. Carbon-12 is the most common. Carbon-13 is slightly heavier. It has an extra neutron in its nucleus. In non-biological material, carbon-13 makes up just under 1% of all carbon, and this proportion is roughly constant. In living things, carbon-13 is consistently underrepresented. The reason is that biological processes, photosynthesis, enzyme-catalyzed reactions, cellular metabolism, preferentially use the lighter isotope. The machinery of life is fractionally biased toward carbon-12 because reactions run slightly faster with lighter atoms, and over billions of cycles this small kinetic advantage accumulates into immeasurable depletion. This bias persists through food chains. A predator has less carbon-13 than a plant because it is eating depleted carbon. A scavenger has less still, and this isotopic signature persists in ancient organic material long after every other sign of life has degraded. Find an anomalous carbon-13 depletion in a Martian drill core, and you have a case to argue in front of a skeptical audience. The same kind of isotopic anomaly exists for nitrogen, for sulfur, for iron. Each element that passes through living chemistry picks up a biological imprint. Together, these chemical signatures constitute a detection method that does not depend on finding a living organism or even a recognizable fossil. It depends only on finding chemistry that has been through biology at some point, which means even Mars in its current cold, irradiated, apparently dead state might still carry a record of everything that ever lived there. Now consider the practical challenge of finding it. The surface area of Mars is roughly equal to the total land area of Earth. We have driven in total a few dozen kilometers across it. We have drilled to depths of a few centimeters. The subsurface environments most likely to harbor extant life, deep brines, geothermally heated aquifers, are kilometers below the surface. We have not sampled them. We have not come close. Our understanding of the Martian subsurface is roughly equivalent to what a team of geologists could conclude about Earth's deep biosphere by analyzing a handful of surface samples from the Sahara. Sending humans would not obviously help. A human crew on the surface of Mars would face enormous constraints: time, supplies, radiation exposure, the sheer logistical difficulty of keeping fragile biology alive in that environment. They would have days, perhaps weeks, of productive surface time before they would need to return. A biological search of the kind that would actually be meaningful, drilling deep, waiting for slow chemical signals to develop, running assays that take months, is not a task for an expedition. It is a task for a long-duration automated system. The rover Opportunity operated for 14 years. Curiosity has been running for over a decade. These machines have patience that no crew could match, and they do not need to eat. There is also the contamination problem. Every spacecraft sent to Mars has been sterilized under strict protocols, baked, irradiated, cleaned, to reduce the risk of introducing Earth microbes. Maintaining those standards with a crewed mission is essentially impossible. Humans carry billions of microorganisms on and in their bodies. The bacteria on human skin are not adapted to Martian conditions and would probably not survive the surface, but they might survive in more protected environments like the interior of a habitat or the warm, compressed atmosphere of a spacesuit. More worryingly, the organisms best equipped to potentially survive on Mars, cold-adapted, radiation-resistant, drought-tolerant extremophiles from Antarctica or high-altitude deserts, are not the organisms that live in human guts or on human skin. The contamination risk from a crewed mission is real, but perhaps more manageable than it intuitively seems. The organisms a human crew would carry are specialists in living on and in humans. They are not specialists in surviving Martian conditions and in environments where they would compete against genuinely adapted extremophiles. They would likely lose. And if we are looking for life of shared origin with Earth, if Martian microbes and Earth microbes are cousins, then contamination becomes even harder to interpret. Finding a bacterium on Mars that looks exactly like a known Earth species might mean we contaminated it. Or it might mean that species evolved identically on both planets from a shared ancestor. Distinguishing these cases would require detailed genetic and isotopic analysis, the question of what counts as evidence, and for what is not as simple as it sounds. There is one more possibility in the space of alternative biochemistries, one worth examining because it comes up so often. Silicon, the element just below carbon in the periodic table, with a similar valence structure capable of forming long chains. The science fiction convention of silicon-based life persists because on paper the idea is not absurd. Carbon and silicon are chemically similar in some ways, but look more closely at what silicon actually does in the universe. At the temperatures and pressures found on the surface of any rocky planet, silicon overwhelmingly bonds with oxygen. Silicon dioxide, quartz, essentially, is one of the most thermodynamically stable compounds in existence. Silicon carbide is nearly as hard as diamond. Silicon, once it meets oxygen, locks into crystalline structures that are chemically inert, beautiful, durable, and metabolically dead. For silicon to do interesting chemistry, you would need to keep it away from oxygen at temperatures where it might remain flexible. In practice, this has never been demonstrated to support anything resembling a living system. The organisms on Earth that use silicon, diatoms, certain sponges do so only as a structural material, the way mammals use calcium in bones. They do not run their metabolism on it. Liquid carbon dioxide is a more interesting alternative. On Earth's surface, carbon dioxide is either a gas or a solid dry ice, but never a liquid, because our atmospheric pressure is too low. Raise the pressure above 5 atmospheres, and carbon dioxide liquefies. It is an excellent solvent, better than water in some respects, capable of dissolving both salts and oily compounds that water cannot touch. Japanese oceanographers have found liquid carbon dioxide pooled on the floor of deep submarine trenches near Okinawa under the pressure of thousands of meters of water above. In those pools, they found microbes, ordinary Earth bacteria that had modified their cell membranes to survive in an environment that would dissolve standard lipid bilayers. Enzymes taken from ordinary microorganisms and placed in liquid carbon dioxide remain stable and active, sometimes more active than in water. This is not theoretical biology. This has been demonstrated in laboratories. Whether life could originate in liquid carbon dioxide rather than merely survive after being introduced to it is a different question and one that remains open. But the point is that the chemical toolkit for life is broader than we assumed even a few decades ago. Which brings us back to Mars and to the honest position that any careful scientist should occupy when facing this question. We do not know whether there is life on Mars. We do not know whether life ever started there independently. We do not know whether any Earth organisms have made the crossing on meteorites and taken hold in subsurface habitats we have not examined. We do not know whether the biosignatures, the isotopic anomalies, the chiral imbalances, are present in Martian rocks because we have not analyzed enough of them with the right instruments. What we know is that the conditions required for life as we understand it, liquid water, chemical energy gradients, shielding from radiation, have existed on Mars, probably billions of years ago on the surface, and possibly right now in the deep subsurface. We know that life on Earth has colonized every environment where those conditions exist, and several where we were surprised to find it could. We know that the two planets exchanged material during the period when life was first emerging on Earth. We know that detecting the chemical traces of ancient or extant biology in Martian rock is technically feasible with the instruments we already know how to build, and we know that the answer matters enormously. Finding life on Mars that is genetically and biochemically identical to Earth life would confirm that biology spreads between worlds and would raise immediate questions about which planet was the source. Finding life with the same basic biochemistry but significant genetic divergence would confirm a shared origin billions of years ago and tell us something profound about the pace of evolution in isolation. Finding life with a fundamentally different molecular architecture, different chirality, different backbone chemistry, a completely alien genetic code, would mean that the universe has produced life at least twice in a very small volume of space, and the implications for the abundance of life in the broader cosmos would be staggering. And finding nothing, conclusively, after deep drilling and long analysis and careful chemistry, would also be important. It would constrain the probability of life's emergence from prebiotic chemistry in ways that a single Earth example cannot. It would not close the book on extraterrestrial life. It would not prove the universe is empty, but it would sharpen the question. The question may no longer be rhetorical. We have the instruments, we have the missions in development, we have, for the first time in human history, the technical ability to actually answer this. Not quickly, not cheaply, not without decades of patient, painstaking, mostly boring science interrupted by moments of extraordinary discovery. But the answer is out there, and it is close.